Okay, so today what we're going to talk about is electron configuration. And electron configurations refer to the arrangement of the electrons around the nucleus. And if we look at any of our atoms on the periodic table that are neutral, if you remember back from when we talked about the structure of the atom and our subatomic particles, any atom that is neutral has an equal number of protons and electrons. So if we look at a couple of example elements, carbon, which is element number 6, should have 6 electrons if it's neutral, and uranium, which is element number 92, should have 92 electrons if it is neutral. Now these electrons are arranged in something called shells. And a shell is kind of like a layer in an onion. If you think of when you cut an onion in half, you've got those concentric circles around the middle. That's kind of what a shell is. Basically, a shell is defined, an electron shell is the distance from the nucleus where the electrons may reside. And these shells, what they do is they actually represent energy levels. Kind of like in the Bohr model. Remember with the Bohr model we had the electrons moving around the nucleus kind of like planets in the solar system. And while that model wasn't exactly correct in terms of how the electrons actually travel, it did have the concept that there were these energy levels, these places where the electrons did tend to be found. So Bohr had a little bit of things right. He just didn't have everything all put together in terms of exactly how they traveled, because they don't travel like those planets. The shells that are lower, in other words closer to the nucleus, represent lower energy levels, and ones that are further away are referred to as higher shells, and they have higher amounts of energy. So how are electrons actually put into these shells? Well, because of the attractive forces and the opposite charges of the electrons and the positive nucleus, they are actually pulled, they're attracted towards each other. So electrons tend to cluster as close to the nucleus as possible. What this means is when we look to actually place electrons into shells, they are going to fill the lowest shells first because they like to have the lowest energy. Now inside of these shells at these different distances, we have another feature of electron configuration that's called an orbital. Now if the shells represent the energy levels, then the orbitals represent the probable position. In other words, when these electrons travel, where we're most likely to find them at that particular energy level. Orbitals are also sometimes called subshells, just because each orbital, we can have different types of orbitals at each shell, and each shell has different types of orbitals present. Okay, so there can be multiple orbitals per shell, and I think it'll actually make more sense when we actually go through this level by level. No matter what level it's at or what type of orbital it is, each orbital can only hold 2 electrons. And exactly where the electron is located in the orbital is determined by both the pulling force of the protons and the pushing force of the other electrons, that repulsive force. What I want to spend the rest of this session with is talking with you guys about combining this idea of shells and orbitals and talking about the number of electrons that we can actually find at each of these. So we're going to start with our first energy level, and our first energy level is our first shell. Our first shell contains only 1 orbital, and that is the first kind of orbital that we find on any level, and that is the s orbital. So the s orbital is found on all of our different energy levels. The characteristics of any s orbital at any shell level is that it is going to be the one that is closest to the nucleus. So that's why it gets filled first. Remember, the closer you are to the nucleus, the lower energy you have. So S are always the first one of any energy level to get filled. If the s orbital is holding its maximum 2 electrons, they actually push each other so that they stay 180 degrees, or in other words, half of a circle, away from each other. So, because the first energy level only has one type of orbital, its maximum is therefore 2 electrons. This is actually what the s orbital looks like, S for spherical. Okay? So you can see you would have, if you had 2 electrons, they would be on opposite sides basically of the spherical circle. Now, because this can only hold 2 electrons, this only explains the electron arrangement for anything up through helium. Okay, because after helium, or after element number 2, we get more than 2 electrons. So then what do? Well, once we've reached that point, then we actually move to the second shell. And that is our second energy level. So once the first energy level has 2 electrons, it is completely full. Any new electron that we would need to place gets pushed away from the nucleus and bumped to a higher energy level, in this case, the second energy level. Our second energy level has 2 different types of orbitals. It has an s orbital, a single one again, and 3 what we call p orbitals. These 3 p orbitals actually have the same shape, they're just arranged differently in space from each other. They are shaped very differently than the s orbital, but even though they're shaped differently doesn't mean that they can hold any more electrons. They can still only hold 2 electrons. So if I look at the second energy level in total, it will hold 8 electrons. The s orbital will hold only 2, and then it has 3 p orbitals, with each that holds 2 electrons. So 3 times 2 gives me 6, and 6 plus 2 gives me a total of 8. And these are what the p orbitals actually look like. They are arranged along the 3 dimensions of our world, okay, x, y, and z. They kind of are like elongated ovals. They almost kind of look like dumbbells. It's usually how I describe them. But this one is the x, that one is the y, and then the z. So when you actually put them together, they're sticking out in all 3 different directions of space. Now, second energy level holds 8 electrons. First energy level holds 2. So 8 plus 2 gets us to neon in terms of electrons, 10. So I can place 10 electrons up to now, which means I'm up to neon. So now what do I have to do? Well, we move out again to another energy level, the third shell, the third energy level. What I hope you guys are noticing is that as we move energy levels, we actually skip down a row on the periodic table. So remember, we were talking about how the periodic table explains a lot of things. Every time I move down a row on that periodic table, I am actually moving out an energy level in terms of where my electrons are placed within the atom. The third shell has 1 s orbital again, 3 p orbitals again, and we add a new type of orbital, and we have 5 of them, and they are called the d orbitals. Now, we know that s holds 2. We know that the 3 p ones hold 6 total. Okay, so 2 and 6 is 8. 5 d orbitals hold a total of 10 electrons. All right, so this level itself, this shell, can hold 18 electrons. So this gives us a total with energy levels 1, 2, and 3 of 28 electrons. So now what? Now I'm at 28. And I want to move on to element number 29, copper. So how would I do that? Well, for any energy level, yes, we have to bump down an energy level again. For energy levels numbers 4 through 7, actually, I'm sorry, that wasn't copper. For any energy level 4 through 7, we add a fourth type of orbital, the f orbital. Okay. Now, with the f orbitals, there are 7 of them in each of the energy levels 4 through 7. So this adds a total of 14 electrons to each of the energy levels, starting with number 4. So energy level 4 is going to have an s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. And so will 6 and 5 and 7. What this allows us to do is to place all the electrons that we would need for any element on the periodic table. Now there are other orbitals, but remember we are filling them so that they have the lowest energy possible. So that's really all we want to talk about at this point. Tomorrow what I will do is I will actually show you how we actually fill these and write our electron configurations, and then we'll have some practice time with that. That will continue into Monday, so that Tuesday we can have our vocab quiz, go over our objectives, spend our day reviewing for your test on Wednesday. At this point in time, with any time left in the period, you guys have to work on your graphing periodic table trends that you need to, because that is due tomorrow. Please remember that this is an individual activity. While you guys can kind of ask questions of each other, you can also ask questions of Mrs. Mateer, but I expect it to be your own work. And just as another reminder, I am around after school today, and I will see you guys then. If not, I'll see you tomorrow.